Hi guys, here is an overview of the problems that you are supposed to work on over the weekend and Thursday and Friday, last Thursday and Friday. So here is the scenario. Let's say example. On the average, American students, college students study about 17 hours per week. That means mu is equal to 17. And standard deviation sigma is given to be 3 hours. Okay. Now, based on this information, as well as one more thing, is normally distributed. Study hours are normally distributed, but I mean bell shape. So based on this information, you are supposed to answer questions of this type. Exactly, not the same questions, but similar questions. So I'm kind of giving you a heads up on how to approach the actual problems. So let's go ahead and find out. So let's do a few of them. So what's the probability that a randomly selected student studies more than, let's say, 18 hours? Okay. Let's make it actually a nice number, 20 hours. Probability that a randomly selected student studies more than 20 hours, and as you know, is bell-shaped, right? Hours are bell-shaped, study hours, which has a mean of 17 mu is equal to 17, and standard deviation is 3. So for some reason, my pen isn't working. So let's try it again. Sigma is equal to 3. So 20 would be somewhere here, right? So you want more than 20 hours. So there'd be this region. Remember, in continuous case, probability is defined by the area under the curve. So you have to convert it into standard normal distribution that has a mean of 0 and sigma of 1. So we go back and forth by using z is equal to x minus mu over sigma, or z is equal to x minus x bar over s, depending on what scenario we are dealing with. Here we are going to deal with this. So corresponding to this 20, there will be a point right here. Let's say z is equal to something, all right? So what we do, we find the z value. Z is equal to x minus mu over sigma. My x value is 20. That's the x. So 20 minus mu is 17, and sigma is 3, which is 3 over 3. That is equal to 1. So your z is actually 1. So this point is 1. So this area is the same as this area. So there's going to be the same as probability of z greater than 1. Now, of course, probability z greater than 1, you can find it from the table, because standard normal distribution table gives you area to the left from the point of interest, which is z equal to 1. So that is to say 1 minus the probability of z is less than 1, which is the same as, if you look it up in the table, it should be 0.8413. That is going to be 0.1587, I guess. Okay, so it is 15.87% chance that someone would study more than 20 hours. Now, this is just the regular case. Now, what if I change the problem a bit? Find the probability that a randomly selected group of students, let's say you selected 49 students for simplicity. So you selected 49 students, and what is the probability that their average average of these 49 students' study hours will be greater than, let's say, 20 hours. Okay, so you can go ahead and do the math here. So in essence, I'm asking you, what is the probability that X bar, the average of these 49 students, randomly selected students, average of their study hours is going to be greater than 20. Now, the distinction between this one and that one is that here you're considering one student that's coming from the population. Here you're considering 49 students. Is more than one, so it's coming from the sampling distribution. That's where the central limit theorem comes into play. The sampling distribution applies to sample size greater than 1. So according to the central limit theorem, first of all, your n is greater than or equal to 30. So regardless of what the initial population is, your sampling distribution is always going to be normal or bell-shaped or Gaussian. So this is something you've got to remember. If your sample size is greater than or equal to 30, regardless of the distribution of the initial population, remember, for the initial population or the original population, the sample size is always 1. Like that's why we just have X as opposed to X bar here, because it's more than 1 sample size. So in the sampling distribution, if sample size is bigger than or equal to 30, the sampling distribution is always going to be bell-shaped. And the two conclusions of central limit theorem are mu sub X bar, that is the mean of the sampling distribution. That means the mean of this guy, mu sub X bar, is the same as the mean of the population, which is this. So it's going to be also 17. And number 2 conclusion, sigma sub X bar, that is the sigma sub X bar, that's the standard deviation of this sampling distribution, is equal to sigma over square root of the sample size. In our case, sigma is 3 divided by square root of n is 49. So that's going to give you sigma sub X bar is equal to 3 over 7, because square root of 49 is 7. So 3 divided by 7, by the way, is 0.428. So I kind of round it to 0.43. Okay, so sigma sub X bar is 0.43. Now, to find the probability that a randomly selected student, a group of randomly selected 49 students, their average is greater than 20. So 17 is here, 20 is here. So 20 is here. Greater than that would be this, right? Now, you have to convert it into standard normal distribution, like the way we did for the regular distribution. Now, let's go ahead and do it for this one, standard normal distribution. So this is going to be mu sub X bar is equal to 0, and sigma sub X bar is equal, sigma sub X bar is equal to 1. By the way, this is the standard normal distribution. I'm just putting mu sub X bar and sigma sub X bar here just to remind you that we are dealing with sampling distribution as opposed to regular distribution, population distribution of the population. And instead of using Z, I'm going to be using Z sub X bar, just to clarify it that we are dealing with sampling distribution. This is going to be X bar, the point of interest. This is the X bar, because why is it X bar? Because we are dealing with 49 students. Okay, so you cannot just say one number. That number is actually the average of those 49 students. So Z sub X bar is equal to X bar minus mu sub X bar over sigma sub X bar. So if I do this, so Z sub X bar is going to be, Z sub X bar is going to be X bar minus mu sub X bar over sigma sub X bar. We already found all of these values. Z sub X bar, X bar is 20. So 20 minus mu sub X bar, we just found it to be mu. Mu is 17. So we have mu sub X bar 17 divided by sigma sub x bar, we found it to be 0.43. So 0.43. So that is going to be 3 over 0.43. And let me do that math for you. 3 divided by 0.43 is going to be 6.97. So z sub x bar is equal to 6.97. If you actually round it, it's going to be 6.98. So let's round it to the next number. So this is 6.98. That is, by the way, z sub x bar. Now let me remind you, this area is the same as this area. So this is the same as that. So probability that x bar is greater than 20, probability that x bar is greater than 20 is the same as the probability that z sub x bar is greater than 6.98 standard deviations. 6.98 standard deviations. Let me pause here and remind you this thing. Look, when we consider 20 for one person, we just moved one standard deviation to the right. However, when we are considering the average of 49 people, their average being beyond 20 is like moving almost 7 standard deviations away, which is way out there for normal distribution. Chances of that happening is extremely small. So keep that comparison in mind. And that's why I use the same numbers. So now this, by the way, is going to be 1 minus the probability of z sub x bar is less than 6.98. Remember, standard normal distribution gives you area to the left, not to the right of the point, to the point of interest. So this, if you look it up in the table, for anything above 3.5, they kind of lump everything together, 0.9999. Which is 0.0001, or there is less than 1% chance that, I mean, not 1%, less than 0.01% chance that the average of 49 students would be more than 20 hours. So which is, by the way, if you multiply it by 100, you get 0.01. So that's the percentage. So 0.01% or less chance is actually probably in reality less than that, because the table even doesn't go to that point, 6.98. So that's what it is. Now, the other scenario I could think of is, let's consider it to be scenario number 3. What if your sample size n is, let's make it 16, okay? You can do it, n is less than 30, obviously, right? So you cannot directly apply the central limit theorem. However, you can apply the conclusions of central limit theorem, which are this, right? Only if the sample of 16 that you are taking from, you're taking this sample of 16 students from some distribution. If that distribution happens to be bell-shaped, then these two conclusions are going to hold true. In this case, yes, it's going to hold true, because I told you the original distribution is bell-shaped or normal or Gaussian. So it's fine. However, had I not given you this condition, let's say I told you, no, we don't know anything about the distribution, normal distribution, or the normality of the population. In that case, you'd say, sorry, we can do it because sample size n is equal to 16, which is less than 30. And the population from which I'm sampling, it is not normal, or at least I don't know it is normal for sure, okay? It's not given in the problem. In that case, you cannot apply these two conditions. In that case, you'll say, we cannot really find the probabilities. So we have no choice but to say that, we don't have enough information about the population to use the central limit theorem. So that's very important. You need to look at the sample size, okay? You need to look at the sample size and then figure out whether I can use it, the conclusions of central limit theorem, or not. Remember, On the other hand, let's say if I said nothing about the population distribution, it could be any arbitrary shape, and I give you n is equal to 49, then perfect. You can use these two conditions, this one and this one, because this is bigger than or equal to 30. So even though we don't know the distribution of the original population, it really doesn't matter. You can go ahead and apply the central limit theorem's conclusions and come up with your probabilities, like as we did here. Even though I knew that it was originally normally distributed, but had it not been the case, I could still have done this calculation and would have gotten the same answer. So this should give you an idea of how to solve this problem. I have gotten several emails from students trying to understand these problems, and oh yeah, it's difficult for me, so I don't know what to do. So that's why I'm sending you this kind of overview thing, okay, on how to solve this problem. So go ahead and work on this problem, and I'm going to send you the Google Drive. Go ahead and upload it, the .pdf extension, okay? If you don't know how to convert it to PDF, just Google it, how to convert an image to a PDF, okay? So take pictures with your cell phone or iPad or whatever it may be, and then you can upload these pictures online and then convert it into a PDF. So once you converted the file into a PDF format, make sure to put your name here, okay? John Doe or something, or Jane Doe or something, okay? Put your name, print is all uppercase so that I can read. Oh, okay, and once you convert it into PDF format, go ahead and upload it in the Google Drive with your name as an extension. Oh, important thing. Name the file as, just put your name, that's good enough, okay? Jane Doe. Name the file as Jane Doe. That way I will know who worked on this problem. All right, good luck to you, and let me know if you have any questions, and then maybe I'll go over the problems again in the class tomorrow. All right, thank you very much. Best of luck to you.